So the first one, all whole numbers are rational numbers. Again, I'd like you to stop the tape and try these first in the warm-up and then check your answers. But I'll now go over the answers. So all whole numbers are rational numbers. So all whole numbers, that's 0, 1, 2, 3, so forth, are rational numbers. Well, every number that I just listed is a rational number, so that is true. Cubed root of 64. Well, 64 is a perfect cube. 4 times 4 times 4 is 64. So the cubed root of 64 is 4. 4 is an irrational number. That's false. Several ways I could fix that to make it true, but I'll just say that 4 is a rational. So is a rational number would make it true. Simplifying the following, so I'm just going to show you the answers for those. So first one's a cube root, so no absolute value. If I do the prime factorization of 72, 8 times 9, 8 is 4 and 2, 4 is 2 and 2, so 2 cubed times 2 cubed times 9 gives us 72. So the cubed root of 2 cubed is 2, and I'm left with the cubed root of 9. And then I have 12 divided by 3 is 4, 1/3 for y, and 4/3 for z. Again, no absolute value because this was an odd root. B, cubed or square root of 125, well, that's root 25 root 5, and that's 5 root 5. So then 12 divided by 2 is 6, 1 divided by 2, 1/2, and 10 divided by 2 is 5. So that's how I got the exponents for each of those variables. Initially put absolute value around everything because it's a square root, but the only one which has an odd exponent is c, so that's the only one that needs to keep the absolute value around it. Okay. Next, after the warm-up, we started on our lesson for the day, which is mostly review from Algebra 1. You learned terms relation and function before. So a relation is a set of points. And a function is a relation, so all functions are relations, is a relation in which for every input or x value, there is one and only one output, y. For every input or x, there is one and only one output, y. So we first looked at some examples with just points. So I'm just going to give a table there with x and y. Such as this one. So if I check the definition, I'm trying to determine, is this just a relation or is this also a function? So if I check the definition for every x, 2, I should have one and only one y that goes with 2. So I have 2 with 3, and then I have that same x, 2 with 6. Well, that doesn't meet the definition because for every x, 2 is my x, I have 2 different y values. So this is a relation only. Okay, this is not a function. So when you're given points and you're checking for whether it's a function or not, check the x column, and you should not have repeated x values unless you have a repeated x value with the exact same y values. So something like this. I'm checking the x column. I see all different x's. And so this is a function, which means it's also a relation, both function and relation. Now, be careful. with this definition, sometimes students will read it and see one and only one output y, so they'll think that the y's cannot repeat. That's not the case. The y's actually can repeat. I have 3 here twice. That's not what it means by one and only one y. It's one and only one y that goes with every x. So like I said with this one, for the x value of 2, can only have the y value of 3. I can't have any other y value with the x value of 2. So when I have that different y value of 6 with the same x value of 2, that's what causes it to not be a function and to be just a relation. But here, I'm allowed to repeat the y's, just can't repeat the x's. So that's a function. Okay, also, you want to be careful though, because we could have something like this. And you don't want to just quickly check the x column and see the 2 twice and say, oh, not a function. You have to then check to make sure that the y values are different and it's not just the same coordinate point written twice like this one is. So I have 2, 3. I see 2 again. So I'm hesitating. I'm pausing here, but I'm not yet going to say no to being a function. I'm then looking at the y. Oh, it's the same point. It's just written twice for some reason. So that is actually a function, because for every x, we have an x value of 2 and an x value of 4. There's only one y value that goes along with that. So that is a function. Okay. Now, sometimes you'll be given tables. Sometimes you'll be given sets. Either way, no matter which you're given, it's kind of the same idea. Okay, so if you're given something like this, okay, same question, is this a function or just a relation? Well, I'm seeing 1 with 4, but I'm seeing 1 with 6. So for that one value for x, I have 2 different y values with that value of x equals 1. So this is a relation only. This is not a function. Okay. Next, we talked about domain and range, or reviewed those terms. So domain means all the possible x values of a relation. Could be a function, but doesn't have to be. And range is all the possible y values of a relation. Okay. Actually, I just remembered something. We need to go back. We did also look at determining relation function if we were given a graph. So we better review that. I almost forgot. So if my graph, here's my xy coordinate plane, is, let's say, a diagonal line, and I'm determining whether it's a function or just a relation, I'm going to do something you learned called the vertical line test, which means I'm going to just draw some vertical lines or run a pencil or something vertical across my graph. And everywhere that the graph, which is this diagonal line, intersects the vertical lines, it should only intersect the graph at one point at a time on each of those vertical lines, which this does. This passes the vertical line test, which means, yes, this is a function. Okay. However, if we have a graph like, let's say, a circle, well, that, if I draw some vertical lines, is intersecting the vertical lines at 2 points on the vertical line. Same thing on this one. So that fails the vertical line test, which means a circle is a relation only. It's not a function. A horizontal line, if I check to see if that's a function or not, well, that passes the vertical line test. So a horizontal line is a function. However, if I'm checking to see if a, let's say, vertical line is a function, Well, if I draw a vertical line on that vertical line, it fails the vertical line test because there are numerous points that are intersecting with the graph on that vertical line at once. So this is a relation only, not a function. Okay. Now, one other thing we did with relation and function before we go back to domain and range, we also talked about if we were given an equation. So something like y equals negative x squared. Well, I can either look at a table for that, or I could look at a graph for that to determine whether it's a function or not. So let's look at a table. I'm going to pick some negatives, 0, and some positives, and I'll substitute in. So if I square -2, I get 4, but then I take the opposite sign, that's -4. Squaring -1, that's 1, but then the opposite sign is -1. Squaring 0 is 0, opposite sign 0 doesn't have a sign, so 0. 1 squared is 1, opposite sign -1, and 2 squared is 4, opposite sign -4. So I'm looking at just those couple values that I filled into my table, and I'm thinking, could let's look at -2 for a moment. Is there a way that when I put -2 in for x that I could get anything other than -4? Well, no, because I followed the rules of math and I'm only going to get -4. There's never going to be anything else besides that with my -2 for x. Same thing with -1. There's going to be no other values besides -1 that I get as an output. Same for all of these inputs. So because I'm not getting any repeated x values with different y values, this is a function. Okay, if we looked at the graph, I'm just going to quickly draw a sketch here. This would be an upside down parabola, and that passes the vertical line test. Therefore, therefore it is a function. Okay, now let's go back to domain and range. So we talked about what they are. Now let's talk about finding them. So I'd like you to put this first graph into your notebook. So we have some just separate points here. 1, 4, the next one is 1 over and 1 down, so that would be 2, 3, and then keep going 1 over, 1 down, and so forth till you get to that last point there at 6, -1. So with domain, we said that's all of the possible x values. Well, you learned that there's 2 different ways to state domain depending on your graph, and range depending on your graph. And sometimes you're going to write the domain as an inequality, but other times you're going to write just the separate values. So it's important to understand when to do which. Here we have these separate points which are not connected. So if I were to describe the domain as starting at 1 and ending at 6, that would be incorrect because that means all values between 1 and 6, like 1.1 and 1.2 and 1.17 and 1.888. Well, I don't have x values at those spots. I only have x values at 1 and 2 and 3 and so forth. So I would not want to write an inequality here. On the other hand, I would just want to write the individual x values of this graph. So let's go ahead and do that. I'm going to write the domain is x equals, and then I'm just going to make a bracket, and I'll include all the x values. Generally, I just put them in order. So 1, 2, 3, 4, 5, 6. They don't have to be in numerical order, but that's usually what I will do. And then a bracket to end it. And that's the domain. Okay, again, not an inequality here because I don't include all those decimal values, just the 1, 2, 3, 4, 5, 6, and so forth. Range. So range, I'm looking at all the y values, so I want to look at the lowest y and go to the highest y. Because it's range, I'll write y equals. I'm going to do the brackets again because we don't have the points connected. The lowest is -1, and then we have 0, and then 1, and then 2, 3, and it looks like it's ending at 4, and then my bracket to end the set. Let's take a look at the next one. So this time we have, here I'm looking, we have an open point at -1, -2. We have it connected. We have this line segment, so it's connected, and then that point on the right is filled in, and it's at 3, 1. So domain here, now I don't want to state separate values because we have the points are connected. So we will use an inequality. So when you're writing domain and you're using an inequality, you're going to put the x in the center, and then you're going to put the less than symbols on either side. Now we know when we read this, we're going to say x is greater than whatever's here and also less than whatever's here, but the symbols themselves are going to be less. So now I'm ready to find the smallest or leftmost x value and the rightmost x value or largest x value. So the smallest or leftmost would be right here. That's the furthest point I see to the left, and the value of that is -1. Now it's an open point, which means not equal, so you won't see me putting an equal sign here. I'm looking furthest to the right, and the x value there is 3. This is a solid point, which is filled in, meaning it does equal. So I will be putting an equals along with the 3. And now I have my domain, which says x is greater than -1 and less than or equal to 3. Now, another way of stating the domain is using what's called interval notation. So I'll show you that as well. Interval notation, you're still looking furthest to the left and the furthest to the right and determining -1 and 3, but you're not going to put the variable, you're just going to put a comma in between. When the points are open and not equal, we will use parentheses. And when they do equal, which it does equal at 3, we will use brackets. So that's the same, these both mean the same thing, whether I'm writing it as an inequality or interval notation, that is representing the domain. Range, so for range I'm looking low to high, I'm putting a y in the center, I'm still putting the less than symbols, but I'm looking lowest to highest, and I am looking at the y values. So -2 is the lowest, it's open, not equal, so I'm not putting in equals. The highest is at +1. It does equal, so I am putting an equal sign. That is my range, which says y is greater than -2 and less than or equal to 1. Putting that in interval notation, -2, comma 1. -2 is not equal, so parenthesis, and 1 is equal, so bracket. Next one. So this time we have array. The point on the left is open and it's -4, 3, then an arrow pointing down. So if I'm looking domain, I'm looking left to right. The leftmost point, first of all, let me put my x, my symbols, my inequality symbols. Furthest to the left is -4. And furthest to the right, this arrow continues to go in the right direction. So it's never going to stop, which means it's heading towards infinity. Positive infinities there on the right. And you can't equal infinity, so I won't be putting equals here. And this was open, so I won't be putting equals there. In interval notation, -4, comma, infinity, can't equal, so parenthesis, doesn't equal, so parenthesis. The range, so I'm writing y, my symbols. I'm looking low to high, low to high. So low, it's pointing down forever. So pointing down forever means it's headed towards infinity, but pointing down is in the negative direction. So it's not just infinity, it's actually negative infinity and doesn't equal negative infinity. Now low goes to high. Highest point is at 3. And 3 it does not equal, so that is the range. Using interval notation, -infinity, comma 3, and neither are equal, so parentheses for both. One more. There's actually 2 more, but we didn't get to that last one, so we'll just look at the parabola. So we have this parabola with a vertex at -1, 1. So domain, I'm looking left and right. Well, there's an arrow pointing on the left and there's an arrow pointing on the right. which means negative infinity is forever to the left and positive infinity is forever to the right. So negative infinity to positive infinity. Negative infinity, parentheses, infinity, or comma, infinity with a parentheses on both. Range, I'm looking low to high. The lowest point I see is at positive 1. And there's a point there. Now, whether I actually physically draw that point or it's just a parabola and I'm telling you that negative 1, 1 is the point, either way, regardless, there is a value, there is a point at negative 1, 1. Again, you don't have to actually physically plot the point to know that. But negative 1, 1 is a point, which means it does equal. So it is, if I'm writing the low, that's 1, and it does equal that. Now, high, it's pointing up forever. So that means positive infinity, and it doesn't equal. So the 1, it does equal, which means bracket, comma, infinity, parenthesis, because it does not equal. And that's where we stop.